Hi, everyone. My name is Tim Stocker, and I'm the Principal Product Manager for energy storage as well as for the TerraMax inverter product line. And I'm here to talk about the concept of operation for the TerraMax family of inverters as well as the H-series power optimizers. For this concept of operation, I'm going to be focusing on the H1300, which is available now. We will provide a future concept of operation for our H1500 at a later point. We have two modules that are connected to the input of each optimizer. And in this example that we're going to be focusing on today, we're going to assume that each module outputs 500 watts at normal operating conditions or maximum power point conditions. And so when you put two of those in series, we have a voltage of 90 volts and then a current in this example of 11 amps, which when you multiply voltage times current to get power, you get 1,000 watts or 1 kilowatt of power with those combined modules in series connected to that optimizer. Now, on the output side of the power optimizer, we're essentially trading voltage for current. So you can see on the input side, we have 90 volts and 11 amps of current. On the output side, we have 50 volts and 20 amps of current, which allows us to have the same power as we see on the input side. And when we trade the voltage and current around, what we're able to do is we're lowering the voltage, which is sometimes referred to as bucking, which allows us to get more modules in a string while still maintaining our input voltage of around 1250 volts, which will become important later. And then with the current, we are increasing the current from 11 amps to 20 amps, which allows you to use a thicker gauge, lower gauge wire, which reduces the total cost and rather than using small gauge PV wire. So now let's go through some examples of operation, and we'll be using 25 optimizers, which have 50 modules connected to those, two modules for each optimizer. So on the screen, we have those 25 optimizers with 50 modules. The inputs connected to each optimizer is 1,000 watts. Remember, as before, we said each module was outputting 500 watts, so combined, there are 1,000 watts. And the effective input voltage is 90 volts at 11 amps, which equates to 1,000 volts. When you combine the power from all of these modules that are connected to the optimizers, we have a string power of 25 kilowatts or 25,000 watts. And as I mentioned before, the nominal input voltage of the TerraMax inverter is 1,250 volts. So let's do a pre-check before we move on. If the nominal string voltage is 1,250 volts and we have 25 optimizers under normal operating conditions where all the powers are the same, each output voltage of the optimizer should be roughly 50 volts. Now let's figure out our string currents. Because the optimizers are connected in series, just like the panels are connected in series, the current will be the same for the whole string, but the voltage could fluctuate between each optimizer while still maintaining the string voltage of 1,250 volts. So let's take our string power, which is 25 kilowatts, divide that by 1,250 volts, and we get 20 amps. So 20 amps is our string current. Now let's figure out the voltage of each optimizer. So we take the input power, which is 1,000 watts, we divide by our string current, which is 20 amps, and we get 50 volts. Now, as noted, this matches up with our pre-check because the system is operating under normal circumstances. So what we do is we sum up all the voltages because they're in series. We sum them up. We have 25 optimizers, which are all outputting 50 volts. That equates to 1,250 volts, which is what the nominal voltage of the TerraMax is. So now let's look at a case where you have shading or potentially you've even had degradation on the module or soiling, which would equate to a lower output power. So in the case of this example, we have 500 watts. As you can see, the input voltage and the input currents coming from the modules to the optimizer has changed. Now the input voltage is 50 volts and the input current is 10 amps, which equates to 500 watts. Now, because we have 500 less watts than we did in the first example where we were operating under normal conditions, our string power has now been reduced to 24,500 watts or 24.5 kilowatts. Because of that, our effective string current has changed. So now we take 24,500 watts divided by 1,250 volts, and our new string current is 19.6 amps. And now let's look at the optimizers which are not connected to a reduced power module. And so for this example, the other modules are still operating at 1,000 watts. We take 1,000 watts, we divide by our new string current, which is 19.6 amps. That equates to a optimizer output voltage of 51 volts. So this is the output contribution voltage of the optimizers that do not see a reduced power input. So now let's figure out the voltage from the optimizer, which is seeing the reduced power input. So we take 500 watts, divide by our string current of 19.6 amps, and we get 25.5 volts. So this is the voltage that's being contributed by that optimizer to the overall string voltage. So now we do our check. We have 24 optimizers, each with 51 volts. Plus we have the one optimizer with 25.5 volts, and we get our nominal voltage of 1,250 volts. So that checks out. Now for the last example, we're going to look at what happens if there's a failure or an anomaly in the module. Let's say a bypass diode has failed, which would effectively not allow any current to flow through, or you have extreme soiling to the point that the module is completely covered and no current is able to flow. So you can see now the input power is 0 watts. So therefore we have 0 volts and 0 amps on the input side of that optimizer. But one important feature of the power optimizers from SolarEdge is that if there is no power on the input side, they still allow current to pass through because they're in series with one another. This allows for a very resilient system, even in the case of a module failure or of extreme soiling. So because we are no longer seeing any power from those two modules, our new effective string power is 24 kilowatts or 24,000 watts. And we still have a nominal voltage of 1,250 volts. So let's calculate our new effective string current. It's 24,000 watts divided by 1,250 volts brings us to 19.2 amps. So this is now the effective string current that's going through all the optimizers. Let's now calculate the voltage of each optimizer that has its full normal operating power. So it's 1,000 watts divided by the new string current of 19.2 amps, which gets us to 52.1 volts. So this is the contribution voltage of each optimizer that has its full normal operating power. And then in the case of the optimizer which has no power, this is a fairly obvious calculation, but we're going to do it anyways just for the sake of this demonstration. We have 0 watts divided by 19.2 amps brings us to 0 volts is what that's contributing. Now, again, because it's still allowing current to flow through, the voltage in the end, it's not contributing voltage, but it's still allowing current to flow through, so it's not interrupting any of the power flow. So we'll do our final check. We have 24 optimizers, which are outputting 52.1 volts, plus the one optimizer, which is at 0 volts, so it's not contributing anything. That brings us to still 1,250 volts, which is the nominal input of the TerraMax inverter. So with our demonstrations over, let's look at the key takeaways. So with the TerraMax and H-series power optimizers from SolarEdge, they're engineered to maximize power production at every level of the system, maintaining that stable 1,250 volts that the TerraMax needs in order to provide its resilient power output, provides that reliable operation while delivering the most continuous energy generation, even under extreme conditions like extreme soiling, module failure, as well as module mismatch or undulation in the land. So thank you for listening. Be wise, optimize.